To prove this, we're going to have to show two basic facts first. That, well, firstly, that, let me just write these down, that Hn is really a subgroup of G, and also that H intersect N is in fact normal in H. Then we'll be able to construct this quotient group here. And we haven't actually explicitly defined what Hn is in the theorem, so let's just quickly do that. Hn is defined to be equal to Hn such that H is in Hn. Oh, undo that. And N is in N. So let's label these facts 1 and 2. So to prove number 1, let's take two elements in Hn. Going by this definition, we can just write H1N1 and H2N2 in Hn. So to prove that Hn is really a subgroup, we're going to have to show it's closed under, well, multiplication. It's got inverses and it's not empty, or it contains the identity element. So to show it's closed, let's just write closed. To show it's closed, I'm going to multiply these together and show that the product is in Hn. H1, N1 multiplied by H2, N2. Let me just move this back. Multiplied by H2, N2. Well, if we write that out properly, we'll have H1, N1, H2, N2. Now we can insert a little term, well, actually in here, in the middle of H1, N1, and use the fact that N is a normal subgroup of G to our advantage. So we can write equals H1, and then we can squeeze H2 inverse in here. Now this is just 1, so I haven't changed anything, and now I'll continue writing this expression. So N1, H2, N2. But now we come to the fact that N is a normal subgroup of G. So in fact, this part of our new expression is in N. Let's just write that as equals H1, H2, and now this part is in N, so we can just write another element of N, let's say N star, N2, but then this is clearly in Hn. So we've shown that it's closed under multiplication. Now we kind of do the same for inverses. So let's take Hn in Hn, and now we'll write its inverse, Hn inverse. We can expand this out as N inverse H times H inverse. We can do kind of the same thing. We can put in H inverse H before this term. And again, since N is a normal subgroup, we have that this is in N. So we can just write this as H inverse N prime, just another element of N. And again, this is in Hn. So we've got inverses, and now it is clear that 1 is in Hn too. So we've shown that Hn is indeed a subgroup of G. Now to prove the second statement. Let's move down and make more space. So for the second statement, let's just remember what we're showing. We're showing that H intersect N is in fact the normal in H. This time it's H, not G. So this is a bit easier than the first thing we showed. Just take an element X in H intersect N. Now by definition we know that x is in H and x is in N. And we're showing normality in H. So we want to kind of consider the element H, X, H inverse. If this is an H, we'll know that H intersect N is normal in H because X, we've picked X to be in H intersect N, and if this whole element is in H intersect N, then we'll know that it's normal in H. Well, this is definitely in H because X is in H, since X is in H. Also, X, well, this same element, this is also in N, since X is in N. X is in N, H is a subgroup of G. So since N is normal in G, and this is an element of G, we know that this whole element is in N. So yeah, this is an N. But now we see that H inverse is in both of these, so it's by definition in H intersect N. And that shows us that oh no, I've written the wrong thing. What this shows us is that, well, this shows us what we were trying to show. And it's also worth mentioning that H intersect N is indeed a group because it contains elements which are both in H and N. But both of these are groups, so H intersect N is clearly also a group. Now we come to show the actual theorem. So, well, I didn't label it I didn't label it number 3, but actually I'll just write this out. So now we show that Hn modulo n is isomorphic to H modulo H intersect n. To do this, well, in my opinion, the nicest way to do this is to define a homomorphism, and then we'll end up using the first isomorphism theorem. So, alright, define well, we don't know it's a homomorphism yet, but it will be. So define phi going from H to Hn mod n. And well, what does this do to the elements of H? It takes them from H to something in there. So just generally we'll write H, the same element H times something from N, and then since it's a quotient group, we'll write that thing timesing the normal subgroup as well. But now we know that N is in N, so we can just write this as H and then the normal subgroup N, because you can think of it as N getting absorbed into the actual group N, because N is an element of N. So yeah, we've got this, well, what we think is a homomorphism. So let's show it's a homomorphism. So take xy in H. Now this equals x n y n by the definition of the mapping we gave up here. But now we know that this is just x, y, n by how we compose the elements of quotient groups. Actually, no, this should have been the other way around. I'm sorry. So this is x, y, n, but then we know because of how we compose elements in quotient groups that this is the same as that. and then this is the same as that. So we indeed have that phi is a group homomorphism. Now we want to figure out, because I said we'll end up using the first isomorphism theorem, we want to figure out what the kernel of phi is. So this isn't too tricky. We write kernel of phi. And what is the kernel of phi? Well, it's all of the h's, elements h in the group H, such that phi of H equals the identity in where we're mapping to, so the identity in Hn mod n. Let's just write this out again. H and H, such that, well, what's the effect of phi on H? Well, it's just Hn. And what's the identity element of that quotient group? Well, it's just n. And by what I said previously, we know that this equality only holds, this is at H by the way, this equality only holds if H is an n, so let's write that explicitly. H is an H, such that n is in n. The above will be true if n is in n, but then this is just by definition H intersect n. So we know that the kernel of phi is H intersect n. Finally, we need to show that phi is surjective, because then we will know that the image of phi is this group here, this quotient group. Now we show phi is surjective. And how do we do this? Well, this is pretty trivial, to be honest. We just take an element in our target space. So let's say we take H star in, sorry, not just H star n in our space Hn mod n. And now we want to find something that maps to it under phi. But this is clearly just H star. But phi maps H star to H star n. So phi is surjective. So image of phi is equal to the target set Hn mod n, or the target group, if you will. But now, by the first isomorphism theorem, well, let's write it down. So the first isomorphism theorem tells us that, what does it tell us? Well, it tells us, in our case, that H modulo the kernel of phi is isomorphic to the image of phi. Well, from before, we had that the kernel of phi equals H intersect n, and we just showed that the image of phi is Hn mod n. So we have that H modulo H intersect n is isomorphic to Hn modulo n,